Hi, my name is Gregor Geršak. I'm coming from University of Ljubljana, from Slovenia in Europe, and I will present our study titled Physiology-Based Patient Simulator for Blood Pressure Meter Testing. Let me just share the screen. Okay. First of all, I have to stress that this is not my own work. There are a lot of people working on this subject. People they are enlisted here, but they are from not only from Slovenia, but also from Austria, Poland, Bosnia, Portugal, Ireland, Germany, Slovak Republic, and Czech Republic. And we are together, we're working on a project called Developing an Infrastructure for Improved and Harmonized Metrologic Checks for Blood Pressure Measurements in Europe, which is written here. But basically, what we are doing is we are concerned about blood pressure meters testing in Europe. So the whole talk will be about blood pressure. There are two basic approaches for measuring blood pressure, and one is the Korotko or Rivarocci standard classical auscultatory principle, and the other one is oscillometric principle. Oscillometry was basically predating Rivarocci-Korotko auscultation method by a couple of years, and it's in clinical use since 1980s. The thing is, it's really simple. It does decrease the observer's error, and it does not contain any neurotoxic materials like mercury, which is usually in classical mercury in glass sphygmomanometers. But it does have some problems. And the basic problem of any oscillometric blood pressure device, such as the one here on the screen, is that it contains an algorithm. This is basically a box which has a pressure sensor in it, and this pressure sensor measures the pressure in cuff. And then it uses a special, usually proprietary algorithm, a mathematical function, calculating algorithm, which calculates the resulting systolic and diastolic values of blood pressure, like 143 over 82 in this picture. And the whole problem is this algorithm in the middle. Because if you wanted to test such a device, whether it's accurate or not, you have to know how the algorithm works. But you usually don't, because none of the producers is so stupid to tell you what kind of algorithm they used in their device. Basically, oscillometry works like this. You pump the cuff pressure up, and so you go up, 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 and then you deflate the pressure according to some trend. And during this deflation, there are these special spikes, these oscillometric pulses in the cuff pressure. And what these devices, the oscillometric devices, do, they measure these oscillations. And using this oscillometric envelope, they can calculate systolic and diastolic blood pressure. But the algorithm is hidden. Not only this, but there are a lot of error sources when you measure blood pressure. And basically, if you divide them in three groups, one of the groups would be errors due to the person performing the measurement, the measuring technique, expectation bias, and stuff like this. One part is errors due to the patient, which can be severely white coat affected. And there's another one concerned with the device. And the last one here is important. If it's really important to have, in order to have accurate measurements, to have clinically validated devices. What does this mean? Clinical validations are basically procedures used to validate electronic automatic blood pressure meter. It basically means that these devices are compared to reference devices like mercury in glass sphygmomanometers. And then at the end of the clinical validations, the researchers can say, yes, this device works approximately similar to a classical mercury in glass sphygmomanometer. So it's comparable. And why is this important? There was a study like 10 years ago in Europe, and they found out that only 10% of all the devices which you can find on the market are actually validated, which means 90% of the devices were not even tested whether they are accurate or not. But this was 10 years ago. After 10 years, we have here's numbers from an Australian study from 2020, and they found out that 80% of upper arms devices only were validated, meaning that the vast majority of devices we can find around ourselves in our everyday life are not even checked by medical staff. And clinical validation are basically procedures how to compare the unknown automatic device, written like blood pressure meter here, and how this is compared to the classical sphygmomanometer. This is usually done sequential, can also be done at the same time, the comparison, and so on and so on. The differences in left and right arm, differences in blood pressure has to be acknowledged, and usually the reference device is not only one, it's only one cuff, one device, but two stethoscopes for two medical experts which independently measure the blood pressure of this person, and then some average of these two measurements is then said that this is like the reference value, which is compared to the value displayed by the device. This is how the clinical validation works. And there are a lot of protocols how to do this. The main is ISO 81062-2. But usually, I mean, the European, American, British, German, and so on protocols exist. Usually, two are the most commonly used: the ISO protocol or European Society of Hypertension, ESH, are the two basic ones. Okay, moving on about clinical validations. First of all, they are time-consuming, they are logistically problematic, and they're expensive, and they're performed in clinics. And one of the biggest problems is also the population pool. So the persons you need to compare these devices on, these persons usually have to be 85 people, also 33 in one protocol, but 85 people, and they have to be young and old and men and women and obese and thin and hypertensive and normotensive and so on and so on. Like, one of the basic problems is you have to find at least 8 people having blood pressure 180 over 110, which is like for the Western countries almost impossible to find. Anyway, clinical validations are quite a logistically and expensive activity, and now the whole basic of my talk will be actually starting. Mainly, patient simulators are devices which are could maybe be an alternative to clinical validations. This, on the left side, this is one of the patient simulators. Patient simulators, there are a couple of big commercial ones here, but basically they are electromechanical devices that generate pressure pulses. And the whole purpose is, if they're basically more practical substitute for clinical validation of blood pressure meters. Usually we can find two types of patient simulators. Patient simulator is the yellow artifact here. One type is limb simulator, which just simulates a human limb, upper arm. And the other one is waveform simulator. Waveform simulator just generates oscillometric pulses, which are then fed to the tube between device and its cuff. And the vast majority of commercial simulators are the waveform simulators. If I show this picture again, oscillometry is dealing with the oscillometric pulses. And these pulses are the thing that simulators produce. Their output are these pulses, and this is then fed between the cuff and the device itself. There's another picture. These devices actually pump the air pressure in the cuff up, then deflate, and then these oscillators occur. They do actually occur also on the way up when the pressure is building up. And this is some of the commercial devices use also these oscillometric pulses to estimate where the systolic and diastolic pressure will be. I have a short video here, how testing using a patient simulator works. So this is the patient simulator. This is the device. And when we start the device, its own pump starts inflating the pressure. The pressure goes up. And at a certain point, the device starts deflating the cuff pressure. And here, at a certain moment, the oscillations occur. And these oscillations are generated by the simulator, by this device. And these are simulated exactly at a certain blood pressure. And at 100/65, so this simulator is set to 100/65 with pulse rate, heart rate 80. This is something which this device should show. And it displayed, there was a bit of error, not a lot. So it was set to 90/60, and the device showed 91/62, meaning the systolic pressure was, the error of systolic pressure was 1 millimeter of mercury, and the error of diastolic pressure was 2 millimeters of mercury. This is the way a simulator can be used to test the device. And the thing is, this device, this way of testing incorporates all the errors of the algorithm which is in this device. Okay, so basically the advantage of every simulator is that there are electromechanical devices and they are extremely stable and repeatable as compared to the extremely variable physiological blood pressure. The disadvantage is that these simulators themselves generate these pressure pulses, which have an artificial form. They're not exactly like a human heart would generate the device. So there are pros and cons, and at this moment, they cannot be used as a substitute for clinical validation. You cannot test accuracy of the device using this. That's why it was decided that we build an advanced physiology-based simulator. This is this box here. It has a special mechanical device which produces pressure pulses, which are then fed between the cuff and the device. And the thing is, this device incorporates a database of actual living persons, some 600 of them, which were basically measured. Their waveforms were measured in the hospital, and meaning that we actually have like a couple of hundred people with different blood pressure levels, different heart rates, different clinical status, and we have their own waveforms for the blood pressure. And at the same time, we also have mercury and glass reference values of their blood pressure. And so basically, this advanced simulator is like a commercial simulator, but it does not have artificial signals. It does not produce artificial signals. It does produce physiology equal signals. I have another video here showing how simulation goes. So this is the blood pressure meter. We started its pressure pump, and then this device starts to generate pressure pulses. This mechanical device here generates these red signals. And this is exactly like human heart, which is pumping blood in heart rate frequency. And at the end, this device showed a value. And the only thing we need to know is which person, what was the blood pressure of this person, and then compare this to the blood pressure which is displayed here. And again, we get error of this device. This is basically the cuff pressure of this measurement. So it inflates and deflates. And at the same, here is the opening valve, which deflates the cuff pressure. And here are the oscillations. This red curve here is basically just oscillation. So this trend subtracted and amplified, and then you see first you have a couple of fast oscillations on the way up, and on the way down there are these oscillations. And the most important thing is that these are signals of a living person, and this person, which was numbered 599, so it was almost 600th person. This person had blood pressure 150/91 with heart rate 64. And this is the goal of this device should show these values. So basically what we did in our paper, we used two simulators, this advanced simulator, which had physiological data incorporated, and a commercial one. They were both set to the same values. This was set in such a way that any device plugged into the simulator should show 143 millimeters of mercury, 95 millimeters of mercury diastolic, and 60 heart rate. And then we found a hypertensive person having almost the same blood pressure and heart rate values. And what we did, we used two different devices. One device was clinically validated automated sphygmomanometer, which is one of the upper class device. And we tested this device using both the commercial and advanced. And the simulator settings are written here. The device showed this, and what we can find out is that this validated blood pressure meter is actually not far away from the commercial from both simulators, meaning that its error is under 3 millimeters of mercury, which is also a limit. So any device in use, at least in the European market, should never have errors larger than 3 millimeters of mercury. So this worked. But then we used another device, and this was a low cost, really not expensive device, also an upper arm device, and we used it again with the commercial device and simulator and the advanced simulator. And what we found out is that at commercial simulator, the device was actually pretty good. 3 millimeters of error in systolic and 2 millimeters of error in diastolic pressure, which is okay. But when we used the real life physiological signals by a living persons, this device, which probably has not so complex mathematical algorithm built in, had actually huge errors, and these errors were in the order like 15 millimeters of mercury, and meaning that this device is not recommended to be used. But you couldn't see this with the commercial simulator. So all in all, what's the conclusion? The conclusion is that if we think that if we have an advanced, complex, physiological-based simulator, it might be useful as a substitute for clinical validation. Not commercial devices, probably not, but this might be. And as a conclusion, we found that the physiology-based simulator is one of the cornerstones of the reliable testing of blood pressure meters, especially because also the algorithm, which is usually proprietary, is checked. Another thing is, we strongly believe, and we will prove that real-life physiological patient simulators could be a substitute for clinical validation. And one of the projects at OSIC, with logo here, is also the same. We want to build a physiology-based advanced simulator, which could be actually used instead of clinical validation. And this is the acknowledgement for the funding, and I thank you for your attention. Thank you.